And the N is the model that you basically put one line on the front and fix the back. So it's just not the nested model of the diamond. So they formula no diamond because it's 0, one diamond is 1. If you have a diamond nested inside of it. Yeah, that was so they for all
Okay.
All right, guys. So now we will continue, and the next speaker is Paul Egre, who will be talking about two logics of indicative condition.
All right. Thanks very much. So this is joint work with Lorenzo Rossi and Jan Sprenger. Both of them are from University of Torino in Italy. And I've had the great luck to visit Monash University over the last 9 months now, visiting David Ripley in the context of the Plexus network. So I'm very grateful for that. I'd like to mention, yes, some of the heavy lifting. That paper comes from Jan, and I hope I can answer sort of the difficult questions you might have. So the leading idea is something we developed in earlier work, but it comes from a long tradition of thinking of conditional reasoning in terms of well, first of all, you restrict yourself to indicative conditionals and you think, well, what does a conditional and what does an indicative conditional tell us? It's a conditional assertion of the consequent. And in fact, this idea dates back to work by Reichenbach and Definiti from the 30s. Simple idea that the conditional takes the truth value of the consequent when the antecedent is true and is indeterminate if the antecedent is false. This is expressed in a slide I'll give next, but our goals is basically to give an account of compounds of conditionals, then show you can assign probability to conditionals without triviality. For those of you who know about triviality results in this domain. But the gist of this paper is to have a logic which is sort of handling two approaches to reasoning. One is in terms of certainty preservation, and the other is about thinking in terms of uncertain premises. So the talk in one slide is you need to remember something from this talk, and afterwards you can actually take a nap. We present two logics of conditionals, C and U. C is for certainty and U is for uncertainty. We're going to show that validity for either can be defined either in terms of probability preservation for a non-standard notion of probability or in terms of trivalence. So similar results are found in the work of Ernest Adams, for instance. As I mentioned, C is a logic of certainty preservation. U is a logic of just high probability preservation, but leaves room for uncertainty. And both logics are also connexive logics of conditionals. So they are non-classical, but they match a natural trivalent generalization of probability and also including, I think, empirical judgments. Maybe I will have the time to show some of them. Okay, so let me say something first about the first two sections of that talk are about just a sort of semantic framework, both for, let's say, assignments of truth values, if you think in terms of trivalence, and then for a non-standard notion of probability. So here is Quine. Yeah, so that's the quote I was referring to by Quine, where he says that an affirmation of a form if P then Q is commonly felt less as an affirmation of a conditional than as a conditional affirmation of the consequent. And I won't read through it, but basically what the rest of the quote says is maybe better expressed in going back to Reichenbach. So Reichenbach noticed that, it's natural to give a conditional sentence the value true when antecedent and consequent are true, false if the antecedent is true and the consequent is false. But if the antecedent is false, then you want to give it the value neither true nor false. The question is, what if you feed back the neither truth value to the antecedent? Then you need to enlarge your table. And in previous work, we looked at two main options for the conditional. On the left-hand side, you find the so-called Definetti table. So that the one proposed by Definetti in a paper from 1935-36. In our published work, we use 1/2 as the symbol for the hash mark, but when you deal with probabilities, it's confusing to have 1/2 for a truth value and 1/2 for a measure of probability. So I'm going to use the hash mark. And on the right-hand side, you have the so-called Cooper table. I think the first occurrence of that table was in the work of William Cooper, who himself was a student of Adams. If you think about it, so the truth tables, they share a common structure. When the antecedent is true, you copy the value of the consequent, and that gives you the value of the conditional. When the antecedent is false, it's undefined either way. But then what would you do when the antecedent is undefined? And one table groups the hash mark with false, right? And another just groups it with true. So there's a certain duality between the two tables. We're actually going for the Cooper table, although a lot of people have gone for the Definetti table. Now, you want to pair this this conditional or one of these conditionals with negation, conjunction, disjunction for a propositional logic. So you could use the strong cleaning connectives, but they raise some issues. For instance, with so-called partitioning sentences. So take a sentence like if A, then B, and if not A, then C. On a strong cleaning analysis of conjunction, the sentence could never get the value 1. Because one of these, let's say, sentences would have to get a value undefined. If you start, let's assume you assign A and C, right? Classical truth values to begin with. Likewise, with if A, then A, and if not A, then A. Then there are other problems with this approach that this principle, if A, then B, or if B, then A, which is classically valid, would also remain. I mean, it could never be false. So depending on the choice you make for validity, let's say these are problematic principles. And the talk is not about these principles, so I'm asking you to trust me, but basically this motivates the choice of these connectors that actually Cooper has in his 1968 paper, sometimes called the quasi-connectives. Negation is still strong cleaning negation. Now, conjunction and disjunction will be undefined only when the two arguments are undefined. And otherwise, they will be classical on classical input. And when one of the arguments is classical, it wins over the undefined part. And there remains also a nice duality between this conjunction and the disjunction. These connectives can be used to solve some of the problems you saw on the previous slide. If you pair them with the right consequence relation, I haven't talked to you about it. What I want you is sort of to remember the shape of those tables, right? If you haven't seen them before. We have strong linear negation, we have these special conjunction and disjunction, and we have the Cooper connective for the conditional, okay? And so our language is propositional logic over these four connectives and interpreted by the Cooper tables. Okay, so that's what we'll need to have a, let's say, trivalent analysis of conditionals. For probability, we need to do something a bit more complicated. The standard representation of probability in the two-valued setting is you take the sum of the weight of the possible worlds where the proposition is true, and that gives you the probability of the proposition expressed by sentence. In the trivalent case, same idea. In this case, but just only with a slight twist. So we're going to assume that we have a countable set of possible worlds, and a measure function we call a credence function. It's defined over this space consisting of the set of possible worlds and associated algebra. And it has these properties. We assume it to be finitely additive, and gives the empty set the measure 0, the whole set the measure 1. And how to define a probability function, which is a non-classical probability function. So I mean, you may not want to call it a probability function. Well, think of it the way you do in two-valued logic. How much more likely is a bet on A to be won than to be lost? That's one way of answering this question. So we can think in terms of betting odds. And so the answer is, in this case, is going to be the ratio between the weight of the worlds where the sentence is true to the weight of the worlds where the sentence is either false or true, so where it's classically defined. Should neglect the worlds where it's indeterminate. So if I call A sub T the set of worlds where A is true, it takes the value 1, AF the set of worlds where it takes the value 0, and A sub I the worlds where it takes the value hash mark. Then you can define the probability of A to be this ratio, right? The measure of AT over the measure of AT plus the measure of AF, right? So it's look at the weight of the true, the one valued worlds, and compare that to the weight of the one valued versus 0 valued worlds together. Now, what happens if, let's say, both of these measures give a value 0? So in other words, if the indeterminate worlds take the whole weight of your credence, then we make the stipulation that the probability is going to be equal to 1, and that's going to matter for some of the results. And it's probably something that can be also tweaked to get different results from the one we get. So we have a non-classical notion of probability. It's similar to the classical by Villain 1. It satisfies some axioms. So yeah, if you add these connectives, right, to the language, which I haven't so far, then the probability of top is going to be 1, probability of bottom is going to be 0. Define them the way semantically you expect, right? Top takes the value 1 at every world, bottom the value 0 at every world. The probability of the negation of A is going to be 1 minus the probability of A, unless A is always undefined, in which case the probability of A is the probability of not A is going to be, they're both going to be equal to 1 in this case. So that's one of these exceptions to the standard probability axioms. And in general, so the probability of A or B is less or equal to the sum of the probability of A plus the probability of B. One thing that may surprise you is we do not have that in all cases the probability of a conjunction is less or equal to the probability of either conjunct. And this is due to Cooper's special conjunction. So because this is surprising, I'm going to give you an example. There's a recent, really very interesting paper by Paolo Santorio and Alexis Wellwood, where they talk about assignments of probabilities to conditionals. And they talk about this n-drop rule. Classically, in classical logic, when you have two sentences A and B that are contingent, such that neither one entails the other, the probability of a conjunction is going to be strictly less than the probability of each of the conjuncts, but not in this setting. So consider their example. You have a die if the die landed even, it landed on 2, versus if the die landed even, it landed on 2, and if the die landed odd, it landed on 1. So here, the probability of this conditional, we're assuming, is going to be given by the conditional probability of the consequent given the antecedent. Or that's just something you can define as the probability of this Cooper conditional. Okay. And so the probability is going to be 1/3 for the first sentence. But intuitively, if you think about what the probability of this, just abstracting away from our setting, from this conjunction, or even from the disjunction should be, it seems that it's also the probability that the die landed on 1 or landed on 2, right? Which is also 1/3. So that's actually a very fine, nice, and compelling reason to go with a non-classical notion of probability based on such examples. Actually, interestingly, toward the end of that paper, they sketch the semantics, which is exactly Cooper's semantics, but they don't know about it. We came from the other direction. We had the paper ready, and then we came across that paper. But I can give you an example. If you really want to work out the example, well, you can. So each of these columns here is for an atomic sentence, like landing on 1, landing on 2, landing even, landing odd. And you've got different valuations, right? So the top row is one in which the die lands on 1. So it's also landing odd, right? The second one, it lands on 2, so it's landing even. And then you've got the remaining cases in which it's neither 1 nor 2, but in the half of the cases are even, the other odd. And now you can check this you obtain by the computation of the Cooper table. And now whether you take the conjunction or the disjunction, right, you're going to end up with the same thing. Each time a classical value is going to win over the hash mark. So eventually, when you calculate the probability, the weight of the set of worlds in which the sentence takes the value 1 compared to the set of worlds where the sentence takes the value either 1 or 0, you just add up, right, the probabilities of these two rows. So you get 1/6 plus 1/6. That is 1/3, which is what the intuition told us about this case. Okay, I need to press on. So in general, call evaluation atom classical if it assigns classical truth values to the atoms of a sentence. So in the general case, so sorry, when A and C are classically valued, you're going to be able to derive that the probability of the Cooper conditional is the conditional probability. So that's a derivation of Adam's thesis in a particular case, for those of you who have heard of Adam's thesis. And now comes, so that was all by way of a background, right? We have a non-classical trivalent logic, which actually existed. It is Cooper's, basically. We just have this also non-classical notion of probability. And now, going to go more quickly. So this is not the order of discovery, but more the order of exposition. Order of discovery, we started from trivalent, let's say, as trivalent standpoint, and then thought about probability. But here, let's say we define the notion of C validity to be a set of premises entails some conclusion if and only if for all probability functions as defined, when the probability of the conjunction is 1, the probability of the conclusion is 1. And the other notion is U validity, which says, well, B is a consequence, an uncertain consequence of the gammas. If there's a finite subset of the gammas such that for every probability function, the probability of the conjunction of the sentences in that set is less or equal to the probability of the conclusion. So this is our notion of uncertainty preservation, if you wish. And the main result in the paper is, first, you can show that preservation of certainty is equivalent to preserving the designated values 1 or 1/2 in this trivalent logic. Second result is uncertainty preservation is equivalent to the fact that for every Cooper valuation, the value of the conjunction of some subset of the premises is less than the value of the conclusion. So it's like preserving values 1 or 1/2 from, I mean, you want to preserve the value 1 and you want to preserve the value 1/2. So since I'm running short on time, the proofs are actually not very complicated. But let me show you some interesting features of the two logics. The way we present them is by listing what we call generally desirable inferences in uncertain reasoning. So here you've got several of the principles of, let's say, conditional logics. And then you've got some disputed principles. So whenever you see a cross mark in the table, it means, note that the schemata are represented as using atomic letters. So when we have a plain check mark, we mean that if you allow yourself to value the atomic sentence, the atoms with either 1 or 0 or hash mark, that is valid, no matter what. This says that the schema remains valid only when actually you give when you restrict yourself to atom classical valuations. So for instance, consider modus ponens. Modus ponens is going to end up fully valid in our certainty preservation logic, but it's actually not fully valid in the uncertainty preservation logic. It's only valid if basically here you're assigning classical values to P and Q. In other words, if you have something like, if you replace now these atoms by schematic letters and you assign the letters the value 1/2, so it means there could be conditionals occurring here. So this could be a nested conditional, then you lose modus ponens. But both of these logics have import-export. And for those of you who do connexive logics, and there's a few of you in the room, both of these logics are connexive, right? So the way the conditional plays out with negation is non-classical. Negation jumps over the conditional, and so on. So I won't go through all of these principles, but I want to show you some interesting features. Yeah, if you look at, for instance, contraposition is not valid even in the sort of restricted atomic form that I gave you in the uncertainty preservation logic, but it's actually also invalid in general in the certainty preservation logic. It will be valid if you restrict yourself to atom classical valuations. Why is that? So it's interesting that contraposition fails for different reasons in C and in U. In C, it really fails if you have nested conditionals. An example would be what you have in 4. If you have a 4-sided die, you know, one of these pyramid-shaped dies, whose sides are 2, 3, 4, and 4, and the 4s are blue, this is certainly true, right? If it's even, then if it's a 4, it's blue. Now contrapose this, it becomes so if it's not blue, if it's a 4, then it's not even. And we claim, I mean, you can again do the sort of table, but even from an intuitive point of view, it's less obvious that it's going to be true. However, even with non-nested conditionals, you could have failures of contraposition just because conditional probability fails to contrapose in general in the uncertain case. So we basically, that's the same thing you have in Adams's logic for the conditional that we have in U. And I don't think anyone had noticed, let's say, 2 different ways in which contraposition could fail. Again, the reasons for failure in C and in U are very different. Or to if, it's an interesting principle. So from A or B, Infer if not A, then B. This principle is valid in our certainty preservation logic. It's invalid in U. Edgington has a really nice illustrative example of this. She says, well, if I'm 90% confident that it's 8 o'clock, then I'm at least as confident that it's 8 or 11 o'clock, right? You agree with that? But that does not give me the same confidence that if it's not 8, then it's 11 o'clock. I think it's a very good example. If you're 100% confident that it's 8 or 11 o'clock, then if you're also 100% confident that it's not 8, then you should be 100% confident that if it's not 8, then it's 11, right? So there's this interesting sensitivity of these arguments to your level of certainty in the premise or premises. Modus ponens is the same thing. So McGee has this famous example, counterexample to modus ponens, referring back to the presidential election in the US. Maybe I can give you a simpler version that Santorio has. So consider again a die example. If the die landed even, then if it didn't land on 2 or 4, it landed on 6, and that seems certain. The die landed even, just out of the blue, you would assign it probability 1/2. If you have no information, right? The only thing you know is it's a fair die. Now, if the die did not land on 2 or 4, it landed on 6. You just eliminated 2 cases, and there remain 4, and that's just a probability 1/4. So I think in terms of uncertainty preservation, you lose your level of probability. If you were sure that the die landed even, then you would be able to infer the conclusion of that modus ponens argument. So we really have a parameter there in the approach of conditionals. Other people have made similar observations, but in different settings recently, like Paulo Santorio again, Sven Net also in a paper on Chensky modus ponens. Okay, so let me go to the conclusion. Yeah, if you're interested in terminology for logics, C, in our previous work, we called QCC/TT. It's a mouthful. Q is for the quasi-connectives part. CC is for the conditional by Cooper, also Cooper-Cantwell, because it was also proposed by Cantwell. TT is for this idea of preserving non-falsity, what we call tolerant truth, and work with Dave and Cooperus and Van Roy. U has been called QCC-SS intersected with TT, for SS is preserving values truth, true, and actually Belknap, 1973 already saw that system. So the systems existed, but they were not connected to probability as far as we knew. There are systems in terms of definity. I don't think I have the time to talk about them. And I think I'll just give you the conclusion, which is trivalent semantics interprets indicative conditionals and making conditional assertions. The framework is compatible with different accounts of logical consequence. And as I say, we get 2 interesting, let's say, logics connecting the semantics and the epistemology of conditional reasoning. C for reasoning from certain premises, and U for uncertain premises. And we have, of course, further questions. How do we incorporate modality? How do you deal with counterfactual conditionals? And we only have partial answers to that, but okay, thanks very much.
So much more.
Thanks.
Right, so questions, comments, remarks. Let's go with Wolfgang first.
Well, just, is it on?
I think so. Let's try. Yeah, it should be on.
Okay, just a remark or question concerning the connective property of your conditional. You just
That was here, I think.
yes. So